Hello folks, this is tutorial number 23 in a playlist that's called Dynamic Scenario and Animation Modeling with 3D Experience, and it deals with the force analysis of a slider crank mechanism. Now, in a different playlist, which was called Kinematics Analysis, I did this particular problem, and the link for it is down here, but this did not involve any forces, okay? So for example, I specified the angular speed of the crank and then calculated the acceleration of the piston and the connecting rod, etc. Now, in this tutorial, I will do a stripped down version of what you see on the left-hand side, because as a mechanism is concerned, it really doesn't matter whether we model all these details or not. Of course, it will affect the force analysis, but not the kinematics one. So instead of doing the one on the left, I will do a simplified version of that. And these revolute joint and cylindrical and prismatic are done with very simple connections. And what I mean, for example, is let's hypothetically say this connection here, the revolute joint here between the crank and the conrod. What I have is a line and a line, and the two planes, okay? The plane that you see and the one that you can't see, that makes a revolute joint. Now, the problem is that when you do it like this and in a very sloppy way that I have, obviously there will be crashes here. You can see that this crank is going through the base, and there is a gap here that nothing seems to be connecting to. They are, this line. So as far as the force analysis is concerned for that, that piston, as long as the mass of the connecting rod is ignored, it makes no difference. So obviously I can do whatever is done in this tutorial with the more complicated version that was already done in the kinematics playlist, but that is really not the point of this exercise. So these are the specifics of dimensions and the masses. Notice that the mass of the piston is about, let's see now, 40 times. 4 times is going to be 0.2. Yeah, 40 times bigger, 40 times bigger than the mass of the connecting rod and the crank. Therefore, later on when I compare my results, I can use formulas that are established for the case where the mass of the connecting rod is ignored. Now, uh, as I mentioned to you, the connections such as the cylindrical and the revolute, etc., are done with connection between the line and, for example, on the connecting rod and the piston. This line and that line are coincident, okay? And the appropriate, if it's cylindrical, that's all I need. So all I'm saying is that I don't have pins and holes and things like that. I'm using things of this type. Now, these are the specific dimensions that I'm taking, and the formula. And I'm going to try it for 62.8 rad per second as the speed of the crank, which is 20 pi essentially. And the formula, assuming that the mass of the conrod is ignored, the formula for the what is called force or effective force on the piston is given by that expression. Okay, these you can find in pretty much any machine dynamics book. And if you plot this thing for the data that's given here, you're going to get something like that. That force varies between 1,000 Newton and minus 592 Newton. Now, before I show you the kind of thing that I expect to get on 3D Experience, and we'll go through it, to get that exact force information, I need to use this joint force probe right there, joint force probe. So when you select the joint force probe, you have a choice of using the piston or the conrod, and you're going to get the same, pretty much the same answer. It doesn't matter. I've used the piston, and I'm going to run it with the DASSL integrator. and that kind of a time step. And obviously, as I said, the velocity of 8.8 rad per second, which is 20 pi rad per second. The force on the piston I already showed you, which is this. If you run it with 3D Experience, you're going to get exactly the same thing. Notice that there's 1,000 here. There is roughly minus 592 down there, and it mimics the behavior that you see here. If you look at the torque due to the motion, this is the formula that you see in textbooks, and this is what you get out of 3D Experience, and pretty much they match. Notice that goes between 50 and minus 50, 50 and minus 50, with these other peaks at roughly 40-ish. Okay. Now, if I run the same thing, not with the DASS-L integrated, but symplectic Euler, I get more or less the same behavior, but there are these, spikes that are obviously not obviously numerical. So this essentially is the same graph that you saw there with a lot of noise. Okay, with a lot of noise. Okay, let's go ahead and do that. I already made the parts, and I'm going to create the joints and then do the rest of the problem. So why don't we actually fix this path? So we go to, let's go to force analysis and to the assembly design. We're going to apply a engineering connection here, fix the path. There's the path is fixed. Good, it's fixed. Now let's mount this crank. Let me zoom in for a second. So we're going to get a revolute. We're going to make a revolute. And there are different templates that I can use. I'm going to use this. Let me see now. I'll use this one. Not that it makes a difference, but anyway, I'll use the fourth one right there. Line, line, plane, plane, and for the angle to control, I use plane and plane. So I'm using this line, line, plane, 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 plane for offset. So I'm going to use this line and that line and this plane and that plane right there. And for the angle to drive that crank, I'm talking about these two selections. I'm going to use this plane and that plane. So that determines the position of the crank, basically. Say okay? And no. Let's do another revolute between this connecting rod and the crank. Let me see how I had it in, yeah. So let's go ahead and do that. Another revolute. Same one that you see here, the fourth one. Move this thing out of the way. So this line and that line, and I'll use this plane and the plane back there. Good. And I don't need to control the angle here, so I'm going to delete that and then say okay. And no. Now let's put the create a prismatic joint. So let's go ahead and do prismatic, and what I will do is, I think the way I had it in my slide, let me see how it was. Yeah, so let's go back here. So prismatic, and let's use a template here. And let me see now, I use line, line, plane, plane, and so for example, I can use, I can use this one, line, line, plane, plane. So let me see. I want this line to go with that line, and I want this plane and that plane, and I know I don't need to control this thing, so I delete the last item. And finally, I need a cylindrical between the connecting rod and this. So let me see now, a cylindrical or revolute, but I use cylindrical between line and line. Really doesn't matter between this line and that line. Okay, and I don't need any of these. Delete this, delete that, and you say okay, and say no. So basically what you see here is my mechanism here, and this is what I was talking about. If you look at your model, you see that there's nothing that physically connects these two except for these lines, which makes a cylindrical joint. That's fine. Now, let me update these. Always a good idea to save. Now we're going to go and assign masses. So we go to the mechanical systems design, not experience, design. And then we go to the last item on the right side here, weight definition. Just wait for a second. Notice that I have already defined it, but if not, what you need to do, let me show you what needs to be done if you haven't already done this. Because I have done it, so it doesn't matter. If you look at it here, it says the one for the pass is 4.973. Okay. The one for the piston is 2 kilogram. Piston is 2 kilogram. Conrod is 0.05 kilogram. And crank is also 0.05 kilogram. Now, if you don't know how to assign these things, please just watch the previous video. It shows you how to do that. But I had already done these, so I'm not going to change it. So, okay. So now that we have done this, we go and create our mechanism representation right there. See this? Okay. Yep. Create a mechanism. Oh, creating mechanism under 3D. Oh, that's because I'm in a part. I'm in a part. Go all the way to the top, all the way to the top, so that you're in assembly. And if you're not sure you're not in assembly, if you're not sure in the assembly, then you just switch to assembly design. You'll find out. Let's try it now. Yeah, I was in the part. I can create the mechanism. So there we are. And then your joints, they're all there. Degree of freedom is 1. And can we check it? If I click on the mechanism player, let's get rid of this, by the way. I don't like these blue colors. I have to, if I close this thing, they'll go away. Okay, good. Now notice that as I move the slider, this thing moves. But of course, notice that it does go through the part, but it's okay, because I've done a sloppy job in modeling this thing. So reset all. So what I'm showing, what I just showed you, is this kind of a thing. All right, so we close it. Now we're going to go to mechanical systems experience. It says, should I create a mechanism? Well, we have already done it, so it's already there. You can see that. Say okay. You don't want it. Say okay. Very good. Now let's go and create our motor. And the motor is here, dynamic, see that? Sorry, here velocity, uh, velocity motor excitation. Click on it. You select that revolute, not the revolute, but the command associated with the revolute right here. See that? Velocity motor excitation. What it's expecting you to do is to select that command that we already agreed to between these two planes, right? And I'm going to make it 62.8. That's the speed, rad per second. Okay, and I have not changed anything. I left this thing as default, so this window that you see here is actually right there. Okay, and say okay. Oh, this is 62, not 82. 62.8, and I say okay. Good. And now create a force law excitation. Not that, not that. Right there. Joint force probe. So what I'm showing you is this joint force probe. Okay. You click on that. And which joint do I want? I want the one, for example, that cylindrical one. The cylindrical one, that's this one. It says you can do it for the conrod or the piston. And I said it really doesn't matter here. Here I've used piston, but you can use the conrod. It really doesn't matter. Okay, I use the piston. It'll be the same. And then we say okay. All right. And then we create a dynamic scenario. The velocity we put it in 62.8 rad per second. For the probe, joint probe, joint force probe, you say okay. For parameter, I use the DASSL integrator, and what are the parameters that I'm using here? 0.001, make it, and then going to 0.4. Otherwise, it'll be very fast. So 0.4 second, and another zero there. And then we say okay, and put the cursor here, right click, and go all the way to force compute, or you scroll down here, you go and compute and generate. Either way, from here or from there down below. Just give it a second. Wow, this is too slow. I don't know why. We have to go change some stuff. Let's check something. Let me change something here. Rewind. This is too slow. Okay, so let's go back. Let me put it back to 0.1. Now run it. Now it doesn't go, there's something wrong here with, let's check a few things. First of all, my velocity excitation, I want to double check, make sure it's okay. Oh, rad per second. Blah, 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 blah. Not degree. Rad per second. Say okay. All right, now I'm going to run it. I'm going to put that thing back on 0.01, 001. Say okay. Now run it. Right. When it finishes, we go to results. Don't worry about that warning. Deselect everything. Just show me the force in the, I think it's in the X direction. Oh, no, it must be the Y direction. Right there. 1000, 1000, minus 593, etc. And if you wonder why is it, because remember when I asked for the plot, I asked for the joint frame, and the joint for the joint that happens to be the Y. Okay. Anyway, let's see it again. Let's try it again one more time. So we have a deselect everything and look at Y, right? Right there. Now what I want to show you is that if I change my integrator, there's going to be a problem. So if I double click on excitation, oh, sorry, this one. Double click, and for integrator, I select the simplistic Euler. I think these numbers should match here. This number should match that or smaller, and I run it. This is not DASSL, it's symplectic Euler, and we're going to plot the force at that joint, same thing that we did before. Deselect all, and it was, I think it was here, X, right? Yeah. Actually, let's check the other one. Not that one. Let's try Y. Yeah, you see it goes between 1000 and roughly 590 with all these spikes in it. So you got to be careful. All right, folks, good luck.